Determining the correct number of branch circuits for 240/120 volt three-phase delta system requires a precise understanding of electrical codes and load calculations. Let's break down the process step by step. The primary task is to calculate the minimum number of 20 amp 2-wire branch circuits required for lighting in a 60-foot by 80-foot store. The initial calculation of the area is 60 feet multiplied by 80 feet, resulting in 4,800 square feet, not 4,500 square feet. The store's lighting load calculation is based on Table 220.12 of the National Electrical Code, or NEC, which provides general lighting load requirements for various occupancies. Table 220.12 specifies a unit load of volt-amps per square foot for different building types. For stores, this value is typically 3.0 volt-amps per square foot, depending on the specific occupancy requirements as defined in the NEC. Therefore, the total volt-amps required for lighting is the area multiplied by the unit load, which is 4,800 square feet multiplied by 3.0 volt-amps per square foot, equaling 14,400 volt-amps. Next, the number of branch circuits must be calculated based on the voltage and amperage of the circuits. The system is a 240/120 volt three-phase delta system. A key point to note is that in a 240 volt delta system with a 120 volt center tap, only one phase has the center tap to provide 120 volts. This means the 1.732 multiplier, used for balanced three-phase loads, is not applicable when calculating the load in the 120 volt portion of the system. The reason the 1.732 multiplier is not used is because the 120 volt loads are effectively single-phase loads connected to the center tapped phase. Each 20 amp branch circuit at 120 volts can supply a certain amount of power. To find out how much, we multiply the voltage by the amperage. This yields 120 volts multiplied by 20 amps, which equals 2400 volt-amps per branch circuit. Now we determine the minimum number of 20 amp branch circuits needed by dividing the total volt-amps required for lighting by the volt-amps per branch circuit. This is 14,400 volt-amps divided by 2400 volt-amps per branch circuit, which equals 6 branch circuits. However, it is crucial to understand that this result assumes continuous lighting loads and proper dirting factors. In NEC section 210.19, A1 states that branch circuit conductors shall have an ampacity not less than 125% of the continuous load. This means we must account for the fact that lighting loads are often considered continuous, meaning they operate for 3 hours or more. To account for the continuous load, we increase the total volt-amps required. Multiply the initial result by 1.25. So 14,400 volt-amps becomes 18,000 volt-amps, due to the continuous load requirement. This adjustment affects the number of branch circuits needed. The new calculation is 18,000 volt-amps divided by 2400 volt-amps per branch circuit, which equals 7.5 branch circuits. Since you cannot have a fraction of a branch circuit, you must round up to the next whole number. This results in a minimum of 8 branch circuits. Therefore, the final answer, considering the NEC requirements for continuous loads, is 8 branch circuits. Furthermore, it's important to consider additional factors that might influence the number of branch circuits needed. These factors include the type of lighting fixtures, their energy efficiency, and any specific local codes or requirements that might apply. For instance, if using high-intensity discharge, or HID, lighting, the NEC has specific requirements for the number of fixtures permitted on a single branch circuit based on the ballast volt-ampere rating. Similarly, if using LED lighting, while more energy efficient, it's crucial to account for the inrush current of LED drivers, which can impact the load calculations. Additionally, emergency lighting should be on separate circuits, ensuring it remains operational during power outages. This is usually mandated by building codes and safety regulations. Another factor is the voltage drop. Excessive voltage drop can cause lights to dim and reduce the efficiency of electrical equipment. To mitigate voltage drop, the NEC specifies guidelines for conductor sizing. Increasing the wire size can reduce voltage drop, but it also increases the cost of materials. Therefore, engineers and electricians must balance cost and performance when designing electrical systems. Furthermore, consider the placement and control of the lighting circuits. The NEC requires that lighting be controlled by switches or other control devices. These controls should be readily accessible to occupants. Additionally, consider using energy-efficient lighting control systems, such as occupancy sensors and daylight harvesting systems. These systems can reduce energy consumption and lower operating costs. The calculations should also account for receptacle outlets. Receptacles are required in commercial spaces for various purposes. The NEC specifies the number and placement of receptacles based on the type of occupancy and the size of the space. The load calculations for receptacles are typically based on a volt-ampere per square foot requirement or a specific volt-ampere value per receptacle. Remember, the calculation of branch circuits for lighting in a 240/120 volt delta system requires careful attention to detail and a thorough understanding of the NEC. By following these steps and considering all relevant factors, you can ensure the electrical system is safe, efficient, and compliant with all applicable codes and regulations. In summary, firstly, calculate the total square footage of the store. Secondly, determine the unit load from NEC Table 220.12, typically 3 volt amps per square foot for stores. Thirdly, multiply the square footage by the unit load to find the total volt amps required for lighting. Fourthly, account for the continuous load by multiplying the total volt amps by 1.25. Fifthly, calculate the volt amps per branch circuit by multiplying the voltage 120 volts by the amperage 20 amps, which equals 2400 volt amps. Sixthly, divide the adjusted total volt amps by the volt amps per branch circuit to determine the minimum number of branch circuits required. Seventhly, round up to the next whole number to ensure adequate capacity. Eighthly, verify compliance with local codes and regulations, and account for any additional loads or specific requirements. Considering these factors ensures the lighting system is both safe and compliant. For example, if the store had specific lighting requirements, like display lighting that's particularly energy intensive, an engineer would need to consider these additional loads when calculating branch circuits. Display lighting, especially if it uses older, less efficient technologies, can significantly increase the overall load. In such cases, an engineer might opt for more energy-efficient LED lighting, not only to reduce the load but also to lower operating costs and comply with energy efficiency standards. Another scenario could involve a mixed-use building, where the store is part of a larger complex with different occupancy types. In this case, the electrical system design becomes more complex, requiring careful coordination to ensure each space receives adequate power while meeting all relevant codes and standards. An engineer would need to consider the load diversity of the entire building, meaning that not all loads will be operating at their maximum simultaneously. This diversity factor can allow for some reduction in the overall service size, but it must be calculated accurately to avoid overloading the system. Furthermore, the installation of the electrical system is just as crucial as the design. Proper wiring techniques, grounding, and overcurrent protection are essential for safety. All electrical work should be performed by qualified and licensed electricians who are familiar with the NEC and local codes. Regular inspections and maintenance are also necessary to ensure the system continues to operate safely and efficiently throughout its lifespan. These inspections can identify potential issues, such as loose connections, damaged wiring, or overloaded circuits, before they lead to more serious problems. In addition, consider the future needs of the store. As businesses grow and evolve, their electrical demands may change. It's often wise to design the electrical system with some extra capacity to accommodate future expansion or changes in lighting technology. This can save significant costs and disruptions in the long run. For instance, pre-wiring for additional circuits or installing a larger service panel than initially required can provide flexibility for future upgrades. Also, the selection of electrical equipment is critical. Choose high-quality, reliable components that are designed for commercial use. This includes circuit breakers, wiring, lighting fixtures, and control systems. Cheaper, lower-quality equipment may fail prematurely, leading to costly repairs and downtime. It's also important to ensure all electrical equipment is properly listed and labeled by a recognized testing laboratory such as Underwriters Laboratories, or Electrical Testing Laboratories, or ETL, to verify it meets safety standards. Finally, remember that electrical codes and standards are constantly evolving. Stay up to date with the latest changes to ensure your electrical system remains compliant and safe. Attend continuing education courses and seminars to learn about new technologies, best practices, and code updates. The NEC is revised every 3 years, and local codes may be updated even more frequently. By staying informed, you can make informed decisions about your electrical system and avoid costly mistakes. In conclusion, calculating the minimum number of 20-amp branch circuits required for lighting in a 60-foot by 80-foot store supplied by a 240/120-volt, three-phase delta system is a multifaceted process that requires a thorough understanding of electrical codes, load calculations, and safety considerations. By following the steps outlined and considering all relevant factors, you can ensure the electrical system is safe, efficient, and compliant with all applicable codes and regulations, providing a reliable power source for the store's lighting needs. In addition to the above, it's very important to emphasize the significance of proper grounding in electrical systems. Grounding ensures a safe path for fault currents to flow back to the source, tripping circuit breakers and preventing electrical shock hazards. The NEC has detailed requirements for grounding electrodes, conductor sizing, and bonding techniques. Proper grounding is not only essential for safety, but also for the reliable operation of electrical equipment. Grounding helps to minimize electrical noise and interference, which can disrupt sensitive electronic devices. Furthermore, surge protection is another critical aspect of electrical system design. Surges can damage or destroy electrical equipment, especially electronic devices. Surge protective devices, or SPDs, are designed to divert surge currents to ground, protecting equipment from damage. SPD should be installed at the service entrance and at downstream panels to provide comprehensive surge protection. The selection and installation of SPD should be based on the specific needs of the facility and the level of exposure to surge events. Lightning protection is also important in areas prone to lightning strikes. Lightning can cause catastrophic damage to buildings and electrical systems. Lightning protection systems are designed to intercept lightning strikes and safely conduct the current to ground. These systems typically include lightning rods, conductors, and grounding electrodes. The design and installation of lightning protection systems should comply with recognized standards, such as those published by the National Fire Protection Association, or NFPA. Moreover, energy efficiency is a growing concern for businesses and building owners. Implementing energy-efficient lighting and control systems can significantly reduce energy consumption and lower operating costs. LED lighting is a popular choice for energy-efficient lighting. LED consumes significantly less energy than traditional incandescent or fluorescent lighting. They also have a longer lifespan, reducing maintenance costs. Lighting control systems, such as occupancy sensors and daylight harvesting systems, can further reduce energy consumption by automatically adjusting lighting levels based on occupancy and ambient light levels. Regular maintenance of electrical systems is essential for safety and reliability. Maintenance activities should include inspecting and testing circuit breakers, checking for loose connections, and verifying proper grounding. Thermographic surveys can be used to identify hot spots in electrical panels, indicating potential problems. Predictive maintenance techniques can help to identify and address issues before they lead to equipment failures or safety hazards. Safety training for employees is also essential. Employees should be trained on how to recognize and respond to electrical hazards. They should also be trained in the proper use of electrical equipment and the importance of following safety procedures. Regular safety meetings and drills can help to reinforce safety awareness and promote a culture of safety in the workplace. In addition, consider the Americans with Disabilities Act or ADA requirements when designing electrical systems. The ADA requires that electrical switches and receptacles be accessible to people with disabilities. This includes ensuring that switches and receptacles are mounted at the correct height and that they are easy to operate. The ADA also requires that accessible routes be provided to electrical equipment rooms and that signage be provided to identify accessible features. Finally, it's important to document all aspects of the electrical system design, installation, and maintenance. This documentation should include drawings, specifications, calculations, and test reports. Accurate documentation is essential for troubleshooting problems, making future modifications, and ensuring compliance with codes and regulations. The documentation should be stored in a safe and accessible location and should be updated as needed. Electrical engineering requires detailed information about electrical components. For instance, you have to consider wire gauge for the amperage. Depending on the type of wire, you might have to use a 10 American wire gauge, or AUG, or an 8 AWG wire, or other. The insulation also matters as well, be it THHN, THWN, or XHHW. Each have different properties that affect its usefulness. As well as the wire, you have to factor in the breaker that you are using and if it is adequate for the job. Breakers are rated based on the equipment that it is being used for, like motors. Motors are rated with a service factor. If a motor does not have a service factor of 1.15, then it requires a higher rated breaker. The ambient temperatures also affect the ampacity of the wire. The higher the ambient temperature, the lower the ampacity of the wire. The type of conduit used also affects the wire ampacity. If you have multiple current-carrying conductors inside a single conduit, then you need to reduce the allowable ampacity of the wire. It is always best practice to oversize your wire and conduit. This helps with voltage drop and heat dissipation. You also have to consider the distance from your panel to the equipment, because the longer the distance, the more voltage drop you will experience. When working on any electrical equipment, always make sure that you are following proper lockout-tagout procedures. This will ensure that the equipment is de-energized and safe to work on. Always verify that the equipment is de-energized before starting work. Use a qualified electrician to do any electrical work. Electricity can be dangerous and should only be handled by someone who is trained and qualified. If you are not sure about something, always ask a qualified electrician. In conclusion, I hope this helps you with your electrical needs. Remember to always be safe and follow proper procedures.